Here's the model we're going to be working with. It's the plate model with a hole in it we use in the main course. You can check for dimensions and other data from the lesson folder on the website. I've imported the CAD geometry and now want to go ahead and create an analysis study. We need to set up the simulation add-in by clicking on the Add-ins tab and selecting Simulation. After a short pause, the Simulation tab appears. In the main menu, we can now see simulation has been added. Hovering over will show a menu of simulation actions. We can choose the Options item. Under the Systems Option tab, there are two choices, General and Default Library. We'll stay with the General. The What's Wrong messages are important, so we're going to leave those as they are. The Load Fixture symbol quality is OK. The other settings are fine for us now. Now I select the Default Options tab and the unit options are selected. I will just confirm my units as English inch pound seconds for this exercise. We'll be using SI units in parallel examples. Now I choose Load Fixture and I'm going to resize the symbols to drop down just a little down to 50%. You can go through all this and you can set up colors for all the different loading and constraint attributes. I'm going to make a few changes, including a strong red for force. I happen to like that as my preference. Just click on the Color Edit button and select the color. Now we're going to choose Mesh. We've got two options for mesh quality, Draft and High. This does in fact control the element type rather than the mesh quality, so in this respect it's a bit misleading. Draft quality will create lower order solid elements which are 4-noded tetrahedrals. These elements should never be used in an FE analysis, so we must make sure that the high quality is set, which gives us 10-noded tetrahedrons. It's actually worth checking this option every time you start an FEA model to make sure you never have selected the 4-noded tets by mistake. We will come back to mesher setting options, but for now I'm going to choose Standard. I'm going to use this because I want to do a mesh convergence study starting from a bad mesh. Normally we would use the curvature based meshing, which would give most often an improved mesh, but there'll be more on this in a later video. Just for now we're using the Standard as default, which is perhaps not the best in general. We'll leave the other settings as default for the moment. Now I select Plot Color Chart. I can position the result legend on the screen. I will leave it here for now, but sometimes it's a bit irritating to get too close. We can move it further away. I can also set up a different default color chart for the results. Rainbow is unpopular because it's got purple for low stresses. Grayscale is good for printed reports in black and white. The range can actually be flipped to give light color for low stresses. We can also define the color for stresses above yield for a von Mises plot. This is useful as a linear analysis is invalid with stresses above this cutoff, which is what we're going to be establishing, like a cutoff here. This can remind us of that fact and means we can avoid trying to contour where it makes no sense. Be careful here to adjust the yield stress of the material to the actual value required for certification. Don't use the vanilla default, which will come with the Solidworks system. The default plots in static study results can be set up very usefully. There are three types of stress plot that I use all the time. They can be a little fiddly to set up on the fly once we're actually into an analysis and post-processing, so this is a good opportunity to prepare. The first type is the von Mises stress for plot 1. The result component is already von Mises. The result type can be nodal stress or elemental stress. Nodal stress is the default. This will take all stresses calculated at each node and average them. Remember that each element connected to that node will be contributing, and hence they're all averaged. We won't be able to see any stress jumps across adjacent elements using contour plots. Mesh section is the only way to do that, and we will cover that in a later video. Element stress takes the internal nodal stresses of each element and averages them to one single value. We can see stress jumps between elements using this method, but it becomes quite an aggressive way to do it. We can flip between nodal stress, which is too smooth for my liking, and hide stress jumps, and element stress, which is really way too aggressive. However, if they start to converge towards similar values, then that's a good indicator of a good mesh for the stress gradient seen. We're going to go into that in more detail in the following videos, which look at mesh conversion. The next component I want to set up is the first principal stress, which is also called the maximum principal stress. Next up is the minimum principal stress. And because we're using a three-dimensional model, then we can use the third principal stress, P3. We effectively ignore P2. Finally, we can set up the Cartesian stress. The default is the x direction, and I'm going to be flipping through x, y, and z. I'm not going to be setting one up for each of those. So that's all set up then, and finally we can easily flip between these stress states in any analysis result. I'll be explaining how to use the roadmap, or explain how to create a roadmap for stresses and the other material on the course. So we're good to go, so I hit OK. We are now ready to open Simulation to create a new study to explore mesh convergence, and we'll look at that in a later video.